Hi guys, YouTube user amfan12 wanted to see this synchronous motor in more detail, so let's have a look at it. This is a 1800 RPM synchronous motor, rated 1/4 horsepower, labeled Billantine of Omaha. I think that's actually the parent company of the projector and lamp house manufacturers. But on the bottom it actually says made by Leeson Electric, so they had it rebadged. Projector has this flywheel probably both to keep the speed steady and to stop the motor from accelerating too quickly. And this is solid steel weighing about, I don't know, 8 pounds or so. Thank you, whoever designed this. Someone actually has a brain. And lots of wire length too. And there we go. And at first glance, this doesn't really look any different than a regular induction motor. Let's take a little bit more more detail at the rotor, though. This rotor looks very much like that of an induction motor, and it is actually very similar. The only difference is are these slots here that restrict how the magnetic flux can move through the rotor. Basically, it allows it to easily go in one direction, but makes it hard to go in another direction. I think it's better if I draw this out. Okay, here's a diagram of what's going on here. It's a little bit cluttered, but I'll see if I can explain this. The green is the stator and rotor. These are the coils around the rotor, the poles of the stator. It's not quite exactly how it's built, but this is good enough for an explanation. Basically, these air gaps in the rotor make it so that the flux can easily travel through this way. It doesn't have to cross this air gap when the rotor is in this position, but when the rotor is in the other position, the flux has to cross the air gap, which means it's more difficult. So you'll get less flux, which results in a little bit less magnetic force. It basically means magnetically generated force. That basically means the rotor wants to be in a position more like this compared to this. In reality, it'll only be at this position when it's producing zero torque. As you apply load to the motor, the rotor will turn a little bit relative to this, and the lines of force will turn at an angle, and that's what actually generates the torque. And this explanation is also simplified, just showing the motor stationary. But it's actually rotating. These poles effectively move around if it were a three-phase motor. For a single-phase motor, these coils are effectively pulsing on and off, so the flux appears and disappears. And in that case, the rotor will be in a position such that when the flux is at its maximum, it'll tend to be near this angle or at a slight offset from it. And when the flux is at its minimum, the rotor will have turned to be more in this position, but since there's no flux at that time, it doesn't matter that the gap is in the way. This type of synchronous motor is called a reluctance motor, because that's the name of the effect where just the steel wants to be in alignment with the stator poles. But that won't start the motor. That only works to provide torque when the motor is very close or at its synchronous speed. So what they do is add basically the squirrel cage of an induction motor around the outside, and that allows it to produce torque when it's stopped and when it's at lower speeds. So that's how the motor starts and gets up near synchronous speed before it locks in fully synchronous, and then all the torque is produced by the reluctance, because there's no slip that's required for an induction motor to produce torque. The stator on this motor is exactly like that on any other induction motor. There's no differences there. This motor has two 20 microfarad 240 volt caps in it. One is always connected across the second winding as a run cap. The second is connected through the centrifugal switch as a start cap. If you want to make a synchronous motor but don't have already built one like this, you can actually convert a regular induction motor to be synchronous. All you have to do is grind off a little bit of the rotor, the same number of grinds as the number of poles. So a 4-pole motor you'd make 4 grinds, 2-pole you'd make 2, and that creates the same reluctance effect, although it's not as efficient. But you can, this is extremely useful for things like rotary spark gaps in Tesla coils where you need a synchronous motor. And there's plenty of tutorials online on how to do this if you're interested. Here's the motor running just by itself, not on the projector. I hope you found this video on synchronous motors interesting. Thanks for watching.